In the vast, silent emptiness of interstellar space, something strange happened. Voyager 1, humanity's farthest emissary, began speaking in a language we couldn't understand. After decades of faithful service, its communications became gibberish, a stream of ones and zeros, but in no coherent order. For months, engineers on Earth were baffled. Was this the end for our intrepid explorer, or was it something more? The signal was coming from billions of miles away, a faint whisper across the cosmos. It was a technical problem, a puzzle to be solved. But for a moment, the universe felt a little more mysterious. It reminded us that we are listening to the echoes of our own creation, sent out into the unknown. The problem, as it turned out, was a single faulty memory chip, a tiny piece of hardware, corrupted after nearly half a century of bombardment by cosmic rays. Think about that. A machine built in the 1970s, now farther from home than any other object made by human hands, had a small memory lapse. The engineers at NASA, acting like celestial mechanics, had to diagnose the problem from 15 billion miles away. It took months of painstaking work. They had to send commands that traveled for nearly a full day just to reach the spacecraft. Then, they had to wait another day for the reply. It was a slow, deliberate conversation with a machine on the edge of our solar system. Eventually, they found a solution. It was a brilliant feat of remote engineering. They couldn't replace the chip, of course, so they figured out a way to bypass it. They reprogrammed Voyager's computer systems to store the essential code in other locations within its memory. It was like teaching an old friend a new way to remember things. And it worked. The gibberish stopped. Clear, beautiful data began to stream back to Earth once again. Voyager 1 was back online. It was a testament to human ingenuity, a triumph of problem solving across an unimaginable distance. It showed us that even when our creations venture into the great unknown, we can still reach out and lend a helping hand. This event wasn't just a technical fix. It was a profound reminder of what Voyager 1 represents. It is a fragile, aging machine, braving a frontier we can only dream of visiting. Every signal it sends back is a gift, a postcard from the void. The fact that we can still communicate with it, still nurse it back to health, is nothing short of a miracle. It's a story of connection, a story of our relentless desire to know what lies beyond the next hill, or in this case, beyond the influence of our own sun. Voyager 1 is not just a probe, it's an extension of our own senses, our own curiosity, continuing its silent journey into the cosmic ocean. Let's rewind the clock. Back to a time of bell-bottoms and disco music. The year is 1977. Humanity was looking to the stars. A rare alignment of the outer planets was coming. An opportunity that only happens once every 176 years. It was a chance to send a spacecraft on a grand tour, a mission to visit Jupiter, Saturn, Uranus and Neptune in a single trip. This was the genesis of the Voyager program. Voyager 1 and its twin, Voyager 2, were born from this cosmic opportunity. Their mission was simple, yet audacious. Explore the giants of our solar system up close for the very first time. They were our eyes and ears, sent on a journey of discovery. Voyager 1 launched on September 5, 1977. It lifted off from Cape Canaveral, Florida, riding a pillar of fire and smoke into the sky. It was a moment of incredible hope and ambition. We were sending a piece of ourselves, a robotic ambassador, into the great unknown. The spacecraft was packed with instruments, cameras to take pictures, spectrometers to analyze atmospheres, magnetometers to measure magnetic fields. It was a state-of-the-art laboratory, designed to withstand the harsh environment of deep space. Its journey would be long. Its destinations were worlds we had only seen as faint points of light in our telescopes. The adventure was just beginning. The key to the grand tour was a technique called a gravity assist. Think of it as a cosmic slingshot. As Voyager 1 approached a massive planet like Jupiter, It would use the planet's gravity to accelerate and change its trajectory. It's a bit like a skateboarder using a ramp to gain speed and change direction. This clever maneuver allowed the Voyagers to travel from one planet to the next without needing massive amounts of fuel. It was a brilliant use of the laws of physics. Isaac Newton would have been proud. This technique made the entire mission possible, turning a decades-long journey into something achievable within a human lifetime. So, with its trajectory set, Voyager 1 began its long flight into the outer solar system. It was a lonely journey through the dark. For months, it traveled through the interplanetary medium, crossing the asteroid belt and heading toward its first target, the colossal planet Jupiter. On Earth, scientists and engineers waited. They monitored the spacecraft's health, checked its systems, and prepared for the encounter. The anticipation was immense. What would we find? What secrets were these gas giants hiding? The world was about to see the outer planets in a way no one had ever imagined. The age of planetary exploration was in full swing. In 1979, Voyager 1 arrived at Jupiter, and what it showed us was breathtaking. We had seen Jupiter through telescopes for centuries. We knew about its bands of clouds and its great red spot, but Voyager's images revealed a world of unimaginable complexity and violence. The Great Red Spot wasn't just a spot. It was a gigantic swirling anticyclonic storm, larger than 3 Earths. The entire planet was a canvas of chaotic weather, turbulent eddies, cyclones, and lightning bolts far more powerful than any on Earth. It was a dynamic living world, a fluid masterpiece painted by the laws of physics. We saw that our solar system was more active and more diverse than we ever knew. But the real surprises came from Jupiter's moons. Before Voyager, they were just tiny dots of light. Voyager 1 transformed them into worlds in their own right. The moon Io was the biggest shock. Scientists expected a dead cratered body like our own moon. Instead, they found a world covered in active volcanoes. Plumes of sulfur and gas were erupting hundreds of miles into space. It was the most volcanically active body in the entire solar system. This discovery was revolutionary. It showed that tidal forces, the gravitational tug-of-war between Jupiter and its moons, could generate enough heat to keep a world geologically alive. It completely changed our understanding of how planetary bodies work. Then there was Europa. Its surface was covered in ice, but it was crisscrossed by a network of dark streaks and cracks. It looked like a fractured eggshell. These features suggested that beneath the icy crust, there might be a vast liquid water ocean. And where there's liquid water, there's the potential for life. This single possibility, raised by the fuzzy images from Voyager 1, has driven planetary science for decades. It's why we keep sending missions back to Jupiter, to explore Europa and ask one of the most profound questions we can ask. Are we alone? Voyager 1 didn't just take pictures, it opened up new avenues of scientific inquiry that we are still exploring today. The Jupiter flyby was a stunning success. In just a few months, Voyager 1 rewrote the textbooks. It revealed a miniature solar system, a complex system of rings, moons, and magnetic fields, all centered around the gas giant. It showed us that the universe is full of surprises, that our assumptions are often just a starting point for discovery. As Voyager 1 used Jupiter's gravity to slingshot itself towards Saturn, it left behind a treasure trove of data. It also left us with a new sense of wonder. The solar system was no longer just a collection of planets. It was a gallery of strange and beautiful worlds, each with its own story to tell. After its triumphant encounter with Jupiter, Voyager 1 set its sights on the next jewel of the solar system, Saturn. In November 1980, it arrived. We all knew Saturn had rings. We'd seen them through telescopes since Galileo first sketched them in the 17th century. We thought of them as simple, elegant bands of ice. But Voyager 1 showed us that this was a dramatic oversimplification. The rings were not simple at all. They were an incredibly complex system, composed of thousands upon thousands of individual ringlets. They were braided, kinked, and even had strange spoke-like features that appeared and disappeared. It was a celestial dance of ice and dust, governed by the subtle gravitational pull of Saturn's many moons. The complexity was stunning. The images revealed that some of the rings were held in place by tiny shepherd moons. These small moons orbit on either side of a narrow ring, and their gravity acts like a sheepdog, herding the ring particles and keeping them from spreading out. It was a beautiful demonstration of orbital mechanics in action. We saw that the rings were not a static feature, but a dynamic, evolving system. Voyager 1's instruments also measured the size of the particles, finding that they ranged from tiny dust grains to chunks of ice as large as a house. The Lord of the Rings had revealed its true, intricate nature. Just like at Jupiter, Saturn's moons provided their own set of wonders. The most intriguing was Titan. We knew Titan was special because it had a thick atmosphere, the only moon in our solar system to possess one. But its surface was completely hidden by a thick, orange haze. Voyager 1's instruments were designed to peer through this smog. They found that Titan's atmosphere was mostly nitrogen, just like Earth's. But it was also rich in methane and other organic compounds. This led scientists to speculate that Titan might be a kind of primordial Earth, frozen in time, a world where the chemical building blocks of life were abundant. But the temperature was too cold for life, as we know it, to begin. The flyby of Titan was a critical moment for the mission. To get a good look at this mysterious moon, mission planners had to make a choice. They could use Saturn's gravity to send Voyager 1 on to Uranus and Neptune, continuing the grand tour. Or they could direct it to fly close to Titan, but this trajectory would fling the spacecraft up and out of the plane of the solar system, ending its planetary tour. They chose Titan. The allure of this strange, Earth-like world was too strong to resist. And so, after its close encounter with Titan, Voyager 1's planetary mission was over. Its new mission had begun, a journey into the void, toward the stars. After leaving Saturn behind, Voyager 1 embarked on a new phase of its mission. It was now heading into the vast, uncharted territory of the outer solar system. Its planetary encounters were over, but its journey of discovery was not. Its new goal was to explore the heliosphere. That's the giant magnetic bubble created by our sun. This bubble is carved out of the interstellar medium by the solar wind, a constant stream of charged particles flowing outward from the sun. Everything in our solar system, from Mercury to the farthest comets, is inside this bubble. Voyager 1's job was to travel to the edge of this bubble, and if possible cross it. For years, it traveled in darkness. Decades passed. On Earth, generations were born and grew up. The world changed. But out in the cold and quiet of space, Voyager 1 sailed on. Its speed was immense, over 38,000 miles per hour. But space is so vast that even at this speed, the journey to the edge of the solar system took a very long time. It continued to send back data, measuring the properties of the solar wind and the magnetic fields at the far reaches of the sun's influence. It was a lonely vigil, a single point of light carrying our curiosity farther and farther from home. It was becoming a true interstellar scout. In 1990, at the request of the late, great astronomer Carl Sagan, NASA turned Voyager 1's cameras around one last time. It was time to take a family portrait of the solar system. From a distance of nearly 4 billion miles, it took a series of images of the planets. In one of those images, Earth appeared as a tiny point of light, a pale blue dot, as Sagan called it, suspended in a sunbeam. This single image is one of the most profound in the history of exploration. It shows our world, everything we've ever known, everyone we've ever loved, as a mote of dust in the vast cosmic arena. It's a humbling and powerful perspective on our place in the universe. After taking that final photo, the cameras were turned off forever. There was nothing left to see on that scale, and the power needed to be conserved for the long journey ahead. Voyager 1 became a vessel of pure science. its other instruments still listening to the hum of the cosmos. It was now traveling through a region called the Helios Heath. This is the outer layer of our solar system's bubble, where the solar wind slows down as it begins to press against the interstellar medium. The data from this region was completely new. We were exploring a part of our own cosmic backyard that had never been visited before. The spacecraft was truly on the frontier. The journey through the Helios sheath was long and honestly full of surprises. For years, scientists watched the data, looking for the telltale signs that Voyager 1 had finally crossed the boundary. They were looking for two key things. First, a sharp drop in the number of charged particles from our Sun. Second, a dramatic increase in the number of high-energy cosmic rays coming from interstellar space. The Sun's magnetic bubble acts as a shield, protecting our solar system from many of these cosmic rays. So once Voyager 1 was outside that shield, it should detect a lot more of them. The anticipation in the scientific community was, well, palpable. We were on the verge of a historic moment. Then, in August 2012, it happened. The data showed a sudden and permanent change. The solar particle count plummeted. At the same time, the cosmic ray count spiked. The magnetic field readings also changed, indicating that Voyager was no longer in the Sun's magnetic field, but was now in the magnetic field of the galaxy itself. After 35 years of travel, covering more than 11 billion miles, Voyager 1 had done it. It had left the heliosphere. It had officially entered interstellar space. It was the first time any human-made object had ever reached this milestone. It was a moment for the history books, a triumph for humanity. What does it mean to be in interstellar space? It means that Voyager 1 is now bathing in the material that fills the vast gaps between the stars. It is sampling the gas, dust, and radiation of the Milky Way galaxy itself. It is no longer in our solar system's home, but out in the galactic neighborhood. The data it sends back is completely unique. It is giving us our first direct measurements of the interstellar medium. It is telling us what the space between the stars is actually like. This is not just theoretical physics anymore. This is direct, on-the-spot measurement. It's like dipping your hand into the ocean for the first time after only ever reading about it in books. This achievement is monumental. It represents the culmination of decades of work and the fulfillment of one of the mission's most ambitious goals. Voyager 1 is now our first true interstellar messenger. It is traveling through an environment that is fundamentally different from anything inside our solar system. The density of particles is higher. The magnetic field is stronger. The radiation is more intense. Every piece of data it sends back is helping us understand our place in the galaxy. It's helping us understand the environment that our solar system travels through as it orbits the center of the Milky Way. Voyager 1 has opened a new chapter in the story of exploration. Attached to the side of Voyager 1 is a special package. It's a golden phonograph record, a message in a bottle thrown into the cosmic ocean. This is the Golden Record. It was the brainchild of a committee chaired by Carl Sagan. Their task was to create a message for any intelligent extraterrestrial civilization that might one day find the spacecraft. What would you say? How would you represent all of humanity, all of our history, our art, our science, our music on a single record? It was an incredible challenge. The record had to be a snapshot of who we are, a greeting card from Earth. The contents of the record are a beautiful and diverse representation of our world. It begins with 116 images, showing everything from the structure of DNA to pictures of cities, forests, and people from all cultures. There are diagrams of human anatomy and images of us eating, drinking, and running. Next, there are sounds of Earth. The sound of wind and rain, the cry of a baby, the songs of whales, and the roar of a rocket launch. There are spoken greetings in 55 different languages, ancient and modern, starting with Akkadian, spoken 6,000 years ago, and ending with modern Chinese dialects. It's a chorus of human voices, reaching out across time and space. And then there is the music. The music on the Golden Record is a journey across cultures and through time. It includes Bach, Beethoven, and Mozart. But it also includes Chuck Berry's Johnny B. Good. There's folk music from Peru, a wedding song from Georgia, and ceremonial chants from New Guinea. It's a global playlist designed to convey the range of human emotion, from sorrow to joy, from contemplation to celebration. The hope was that music, the language of emotion, might be a universal way to communicate, a way to say, this is what it felt like to be alive on our world. The record also includes a printed message from the President of the United States at the time, Jimmy Carter. His message is one of peace and friendship. It reads, in part, this is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time, so we may live into yours. This perfectly captures the spirit of the Golden Record. It is a symbol of our hope for the future, a belief that we can overcome our challenges and that our legacy is worth preserving. The Golden Record is a testament to our better angels, sent on an eternal voyage among the stars. Keeping Voyager 1 alive is an extraordinary challenge. Think about it. This is a machine built with 1970s technology. Its main computer has less memory than the key fob for your car. Yet, it continues to operate in one of the most hostile environments imaginable, billions of miles from home. The engineers at NASA who communicate with it are like cosmic archaeologists, working with ancient technology and long-retired computer languages. Many of the original engineers who built the spacecraft have retired or passed away. A new generation has had to learn its quirks and its systems, keeping the flame of the mission alive. One of the biggest challenges is power. Voyager 1 is powered by a radioisotope thermoelectric generator, or RTG. It basically uses the heat from the decay of plutonium-238 to generate electricity. But that plutonium is slowly decaying. Every year, the spacecraft has a little less power to work with. To keep it alive, engineers have had to make difficult choices. They have to decide which instruments to turn off, one by one, to conserve power for the most essential systems. The heaters that protect the instruments from the deep cold of space are among the first to go. It's a slow, managed decline, a race against time to get as much science as possible before the lights go out for good. Communication is another huge hurdle. Voyager 1 is now over 15 billion miles away. A radio signal, traveling at the speed of light, takes more than 22 hours to reach it, and another 22 hours for a reply to come back. It's a 44-hour round trip for a single command. The signal itself is incredibly faint. By the time it reaches Earth, it has a power of less than a billionth of a watt. It's like trying to hear a whisper from across a continent. To pick up this faint signal, NASA uses its Deep Space Network, a series of massive radio antennas located around the world. These giant ears are our only connection to our distant explorer. Despite these challenges, the team has found ingenious ways to extend the mission. When a set of thrusters used for orienting the spacecraft began to degrade, they switched to a backup set, a set of thrusters that hadn't been fired in 37 years. They were originally used during the Jupiter flyby and then went dormant. The engineers sent the command, held their breath, and waited, and it worked. The old thrusters fired perfectly, extending the life of the mission by several more years. This kind of creative problem-solving, this refusal to give up on our old explorer, is what makes the Voyager story so inspiring. It's a story of human persistence against the vastness of space. Voyager 1 is more than just a successful science mission. It has become a cultural icon. It is a symbol of our innate human desire to explore, to push the boundaries of what is known, and to see what lies over the horizon. It represents the very best of us, our curiosity, our intelligence, our ambition, and our hope. In an age where we can often feel divided and small, Voyager 1 reminds us that we are capable of great things when we work together, that we can reach for the stars, literally. It is a testament to the power of science and the enduring spirit of human exploration. The journey of Voyager 1 is far from over. In fact, it has only just begun. It will continue to travel through the Milky Way galaxy for eons. Long after we are gone, long after the Earth itself has changed beyond recognition, Voyager 1 will sail on. Its power will eventually fail, sometime around 2025 or shortly after. Its instruments will go silent. Its long conversation with its creators will come to an end. But its physical journey will continue. It is a silent, ghostly emissary, carrying its golden record, a memory of our world, into the cosmic night. It is our legacy, cast into the future. In about 40,000 years, it will pass relatively close to a star called Gliese 445. But it won't stop. It is not heading for any particular destination. It is simply drifting, an artifact of a long-lost civilization, from the third planet of a star called Sol. Will anyone ever find it? The chances are infinitesimally small. The galaxy is a vast and empty place, but the possibility, no matter how remote, is a powerful one. It forces us to think about our place in the grand scheme of things. It connects us to a future that is almost unimaginably distant. And so, Voyager 1 continues its endless voyage. It is a reminder that we are part of something much, much larger than ourselves. It has shown us the beauty of other worlds and the fragility of our own. It has crossed the boundary into interstellar space, acting as our scout and our messenger. Its journey inspires us to keep looking up, to keep asking questions, and to never stop exploring. The story of Voyager 1 is the story of humanity reaching for the cosmos, and it is a story that will continue, written in the silent language of motion for billions of years to come.